Good morning. This is going to be the third and hopefully the final lecture on the series on Arzela Ascoli theorem. Today it's going to be in the setting of metric spaces. So we will review some of the basic concepts which you will learn, which you will need. The first thing, I assume that all of you know something about compact sets. A subset K of your topological space X, or if you are not acquainted with topological space, it's a metric space X. A subset K of X is said to be compact if you give me any open cover of K, then it has a finite subcover. I can extract a finite subcover for K. Okay, this is a modern accepted definition of compactness. But mathematicians always look for somewhat an easier, simpler characterization of equivalent definitions or characterizations of the concept. For example, in this case, let's look at something which is very closest to our heart, or the set of real numbers with the standard topology, standard metric. Then all of us know a subset K of R is compact if and only if it is closed and bounded. It goes under the name Heine-Borel theorem. All right. So notice that the compactness, which is in terms of open cover, is reduced to something very easy in terms of metric concepts. I have to check it's a closed set, and it has check it is bounded set. That's it. This is somewhat easy. Bounded set means I have to estimate. Closed set means every sequence. Okay. If it converges, then the limit also belongs to the original set. That again may be in some sense analysis estimate. Okay, it reduces to something simpler. Okay, now let us look at R with a discrete metric. Okay, distance between x and y is 1 if x is not equal to y, otherwise 0. Now this is also a metric space. I can ask the same question: when a subset K is compact? Then it's very easy. I'm sure all of you know K, a subset of a discrete metric space, is compact if only if it's finite. You see that? Now it reduces the problem to counting the number. How many elements are there? Somewhat much simpler problem. So you can see, instead of hanging upon one standard definition of compactness, we reduce to some equivalent characterization. Okay, this is what various compactness characterizations are about. Arzela-Ascoli theorem also tries to do the similar thing. Okay, so I will just say a pattern. First thing is, if K, a subset of a metric space, is compact, then it's necessary that K must be closed in X. And 2, K must be a bounded subset of the metric space X. Okay, being closed is a topological notion, being bounded is a metric notion. Okay, these are necessary conditions. So the moment you give me a set which is not closed, it cannot be compact in a metric space. And you give me a subset of a metric space which is not bounded, it cannot be compact. So it's a necessary condition. A subset K of a metric space to be compact, then K must be closed in X and K must be bounded. Good. Okay. Now this kind of Arzela-Ascoli kind of theorem tries to do something better. So I know this is necessary, but is it sufficient? Again, you know the example. If I take R again with the discrete metric, it is closed, right? X is closed in itself, and it's also bounded because the total diameter is 1. All right. Therefore, closed and boundedness is not sufficient. So you are looking for a third condition for a subset K to be compact. This third condition is very interestingly depends upon some kind of uniform behavior of the elements which belong to the space. When you construct a space X, it's not just a subset, it's a set. Okay, it's a set of elements with certain nice common property, like set of continuous functions, set of convergent sequences, or set of sequences such that they are absolutely summable. If an is a sequence, summation mod an must be finite. This kind of examples are there, or functions which are integrable. So the third condition, very interestingly, okay, tries to say if a subset K in such metric spaces is compact, it must be closed and bounded. Third condition is it has some kind of uniform behavior with respect to the property. It may be a bit vague, but bear with me. I hope to explain it. Okay, in a moment. Okay. So, in the case of continuous function, what does it say is, since we are going to work with compact metric spaces, any continuous function will be uniformly continuous. Therefore, let me assume a family of uniformly continuous function. I want to know when it is going to be compact. What Arzela Ascoli's theorem says is it has to be closed. Okay, where these are the things we have to explain. Okay, let me explain that, and then we will give you a proof. And if time permits, I will also explain what is the third condition uniformity mean. Okay, in some other context. Okay, this is usually not done in textbook, but it will be very good way of learning. Okay, let us start sharing the screen. Be ready for an adventurous journey. So the references for what I'm going to do about Arzela Ascoli is my book on metric spaces. Look for a second edition. And to applications of this theorem to functional analysis, you should consult a forthcoming book by me with my joint author Sukumar. It is due to COVID, the publications delayed. I hopefully within a couple of months you should be ready. And the third and fourth are two articles of mine. One is an Arzela Ascoli theorem, another one is compact subsets of LP spaces. These two are expository articles. You can download them from the website URL given. Okay, let us get started. So hereafter I am dealing with only a metric space XT. Right? So as I said, a subset K of X when it's compact implies two necessary conditions, closed and bounded, and converse false. This we have seen. Okay, right. And what we want to do is we want to see in the case of metric spaces, there is a beautiful characterization of compactness. Okay, I will recall them and I'll explain if necessary. Okay, okay. So let me call it the theorem. XD is a metric space. Okay. Then the following are equivalent. X is compact. 2. X is complete and totally bounded. Okay. And third, every sequence xn in X is convergent in X. So maybe I will say a subset K of a metric space is compact. If K is compact, K is complete and totally bounded, and every sequence xn in K, sorry, so I made a mistake. For if give me any sequence xn and K, then there exists a convergence of sequence xn K of X, xn, so that xn K converges to X. That's a limit. That limit must be in K. This is very crucial. Okay, this is very crucial point. Not only it is convergence of sequence, the limit should be in K itself. Okay. Now these are the equivalent. These following are equivalent. Right. Is that clear? Let us look. K is compact. We had already explained what it is. That is, you give me any open cover of K in X, then I can extract a finite subcover. Let us look at the third, which is somewhat easy because it does not require any new concept. Suppose you give me any sequence xn and K, it may not be convergent, but I should be able to find a convergent subsequent x and K. Well, x and K is convergent. Therefore, let X be the limit. Where does X belong to? It must be in K. That is a crucial point. Okay, right. Now, let's look at the second condition, the equivalent condition, which is K is complete and totally bounded. K is complete, I'm sure all of you know. What does it mean? Give me any X, the sequence Xn in K, which is Cauchy, then Xn converges to x and x must be in K, because the metric space, with the introduced metric KD must be complete. That means give me a sequence xn, quotient sequence xn in K, then xn is convergent in K. Xn converges to x is in K. That's what it means by completeness. That's I am sure all of you know. But total boundedness, you might have learned the definition, but let me recall. I will also give some insight into total boundedness. Okay, because that sometimes is lacking. You just look at the definition, you think it's easy, but you don't get an intuition about that. So let us look at. So let xd be a metric space, right? I have a subset A of x. I say it is totally bounded if what happens? Think of it as a backdoor entry. Let me go back. See, these are all equivalent conditions, right? Let us look at one by one. Let me understand, go slowly. In fact, I'm see, I gave this lecture without mic for 45 minutes. Okay. Now I'm repeating the same lecture naturally with less enthusiasm. Okay. And now I want to get out of it. So naturally, the flow is missing. Okay. It's all right. Once in a while, one has to make mistakes and learn. Anyway, let's come back. Suppose I want to say a subset K of a metric space is compact. If I know X is already complete, okay, then what do I want to know? With respect to induced metric, KD is compact. When is it compact? It must be complete and it must be totally bounded, whatever it may mean. Now notice that if K is a subset of complete metric space, therefore K will be closed if and only if with the induced metric, this metric space is complete. I'm sure all of you know this as an exercise. Okay, otherwise it's easy. Therefore, what it says is, if I know the metric space is already complete and you give me a subset K, you want me to prove that it is compact, I can use the second condition. If I want to use second condition, I have to say K is complete. But my observation just now, it said I don't have to prove K is complete. It's enough if we show K is closed and then totally bounded. Do you follow that? Right. So please take a minute, pause, review, and proceed. P R P. Okay, good. Now suppose I know K is subset of metric space XD is compact. Okay. Now according to the above criterion characterization, I know K must be complete, and any complete subset of a metric space is already closed. Okay, good. Now since K is compact, okay, notice that if you give me any epsilon positive, there is an obvious open cover. Okay, for any given epsilon, how many of you can guess? Take the open cover Bx epsilon either as x varies over x or as x varies over k. This will be an open cover for k. Since k is compact, I know that there is a finite subset, call it f equal to x1 to xn, which may be contained in x or it may be contained in k, whichever open cover you took. I am not going to specify that. Therefore, my k will be a subset of union Bx epsilon, where x varies over a finite set. If you don't want to write this way, Bxj epsilon, j running from 1 to n, assuming my set is x1 to xn. This is same as union Bxj epsilon. Okay. So what I have shown now, if a k is a compact subset, for every epsilon, I can find a finite subset x1, x2, xn either in k or in x. It is immaterial. So that my K is contained in the union of the open ball B xj epsilon as xj varies over the finite set. Is that obvious? This is clear, right? That is why I call total boundedness is a backdoor entry. So total boundedness is a backdoor entry. Of what? Of compactness. What does that mean? That means I say a subset A of any metric space, just any metric space, is totally bounded if for every epsilon positive, I can find a finite subset F either in A or F in X. It is independent of this. You should check why. So that, okay, A is a subset of union Bx epsilon where X varies over the finite set. F, and if you are not comfortable with F, write 1 to n, xj, x2, x2, xn. Okay. You understand why it's a backdoor entry? Okay. Now, two things you should notice. First, total boundedness implies boundedness of a set. If K is totally bounded, it's bounded. Why? Because if A is totally bounded, remember, then there exists for any epsilon, for example, epsilon equal to 1 also, okay, A is contained in finite number of open balls. But you know, each open ball is bounded, right? A open ball of radius epsilon, its diameter will be at most 2 epsilon. Therefore, each one of them is finite. Finite union of bounded sets is bounded. Therefore, A is being a subset of a bounded set, it is bounded. So that is obvious. And converse is not true. That's because what we already said. If I take R with a discrete metric, okay, then it is bounded because diameter is 1, not even 2, right? Okay, the diameter is 1 and this is bounded set, but it's not totally bounded because if I take epsilon equal to half, then no number of finite number of open balls because each ball of radius epsilon will be singleton. So finite union will be finite subset. Therefore, it could not be enough. Therefore, it may be bounded, but it's not totally bounded. You understand that? And second, if A is totally bounded and B is a subset of A, then B is also totally bounded. That's again clear because I will introduce a notation. This set B F consisting of x1 to xn for this epsilon, this is usually in literature called epsilon net for A, for K, right? If K is totally bounded for every epsilon, there is a finite set x1 to xn, so that blah blah blah, that x1 x xn is called epsilon net. This is a very standard terminology in literature. Therefore, if F is a finite set, finite, F is an epsilon net for A, then that F will also be an epsilon net for B. Now notice that that's where this F need not be only a subset of B. It could be a subset of A, it could even be a subset of X. According to my definition, it's independent. Okay, it's just a finite set in the full space. It may be a subset of A or it may be a subset of B, it doesn't matter. Okay, and third, this is the more telling one. The third, okay, let us look at a subset K of R or more generally Rn. Okay, I am working backwards for a minute. Okay, okay. Now we know by Heine-Borel theorem, K is compact if only if K is closed and bounded. This is Heine-Borel. Right? Very good. Now, according to our earlier theorem, R or Rn is a metric space and these are all complete. Therefore, K is compact if and only if, look at the second definition, second characterization, K is complete and totally bounded, but the ambient metric space is complete, therefore K is closed and totally bounded. You understand that? Therefore, K is compact if only if K is closed and totally bounded. This is according to characterization, second characterization, just now we quoted, right? Therefore, K is compact if only if K is closed and bounded, which is same as saying K is closed and totally bounded. Therefore, what kind of inference you can get? If a subset K is closed, then I should think it should be bounded if and only if it is totally bounded. Do you understand this? Because I don't know whether K can be closed, required or not required. Okay, so to be on safer side, abundant caution, I will say a closed set K is bounded if and only if it is totally bounded. Do you understand the logic? Yeah, please pause, review and proceed. But actually in practice, you can check if K is a subset of R or Rn, then K is bounded if and only if K is totally bounded. Okay. I will indicate a proof for K in R. Okay. The same proof can be adapted for Rn, or you can argue using Heine-Borel theorem, as I said. So I will give two different proofs for that. One, K is, let us assume, subset of R. Therefore, K is contained in some minus m to plus m in this interval, right? Okay. Now I will show this interval is totally bounded. Therefore, K will be totally bounded because it's a subset of a totally bounded set. Now, if you give an epsilon positive, what I can do is I can form an epsilon interval around m minus m. Then let's look at this point minus m plus epsilon by 2, right? And from this, I can take an epsilon interval. You understand that? Okay. Now again take some point from here to epsilon by 2, okay, and go on. By Archimedean property, you see, after certain stage, I would have overshot capital M. You follow that? Yes? Okay. Therefore, in R, total boundedness is same as Archimedean property. This proof can be extended to Rn also. I hope you will follow. Please discuss with your friends. Make sure you understand. Because this is not mentioned anywhere, but you should have. The same proof can be worked with Rn. Okay. But in the case of general case, if I assume Heine-Borel theorem and the earlier characterization, I can prove that. That's what I just now did, but just for your sake. But I proved it for closed sets. But suppose K is any subset of Rn, then I say it's bounded if only if it is totally bounded. Okay. Now K is bounded. Therefore, look at K closure. Okay, this will be closed set, and it will also be bounded. Therefore, by Heine-Borel, okay, K closure is compact by Heine-Borel. Okay, by my characterization, therefore K bar is okay complete and totally bounded. That is my second characterization. Now K is a subset of K bar, and K bar is totally bounded. Therefore, that implies K is totally bounded. Okay, this is a quick proof. Okay, but the one which I indicated using Archimedean property will be very insightful proof. You will see why it fails, why it works. Okay, good. Let us grant it. That's good enough. Okay. So I hope these are the preliminaries I needed. If necessary, I'll come back. Okay, let's not worry about. Okay. Now, what does Arzela-Ascoli theorem say? Arzela-Ascoli theorem wants to talk about characterizing compact subsets. See, we had already characterized compact subsets in R and compact subsets in a discrete metric space. Right? Now, I want to characterize compact subsets of something special. So, let X be a compact metric space. Okay. And let's look at C of XR. These are all continuous functions which takes values in R. The proof which I am going to work will also work with all continuous functions from X to complex numbers. or it will also work from compact metric space X continuous maps from X to Y, where Y may be a complete metric space. Okay, completeness may not be needed, but just to be on safer side with abundant caution, I will simply assume Y is also complete. Okay, so the proof which I are going to give, Arzela Ascoli theorem, will work for any of these cases, but let's stick to this. Okay, real valued continuous function on a compact metric space, right? Now suppose F is a now I want a metric, right? I want to make a matrix on this, so let me not worry about. Okay, X is compact metric space. So I'm sure all of you must have heard, but let us look at, there is what is called a subnorm on this space. So you give me any continuous function F, yeah, F be a continuous real valued function in a compact metric space, F will be bounded. Therefore, let us look at the collection mod Fx as X varies over capital X. This will be a bounded set because F itself is a bounded function and this is non-empty. Therefore, the supremum or LUB, okay, of this subset of real numbers, non-negative real numbers exists. That is what is denoted by standard notation, maybe subnorm or infinity norm. Okay, I'll simply use, because we are not going to deal with any other norm, so I'll simply say. Okay, if you don't understand what is norm, forget it. Okay, so I want to define the induced metric D distance between F and G. By definition is norm of F minus G, the difference of the norm. But this is, you can ignore the norm, you can simply say this is nothing other than least upper bound of mod Fx minus Gx as X varies over the compact metric space X. This is the distance. So this defines a metric. Okay, therefore I have the metric on Cx. This becomes a metric space. This metric we will call subnorm metric. We will also call it uniform metric for a reason to be said soon, to be understood soon. Now, since this is a metric space, okay, I want to understand, if you give me a sequence F1 and F here, when does F1 converge to F? It is a trivial exercise to show F1 converge to F if and only if F1 converge to F uniformly on X. So this is convergence. This convergence is with respect to the metric D, F1 converges if and only if F1 converges to F uniformly on X. So this is a topology, F1 converges to F in D, F1 converges to F uniformly on X, you are seen in analysis. Okay, these two are connected now. You understand that? That's very easy, because what does it mean? In fact, this you have seen this without introducing the metric in your real analysis course. You might have seen define Mn to be supremum of mod Fn of X minus F of X as supremum varies over the set X. Usually it may be interval. Okay, this goes to 0. This is nothing other than distance between F1 and F according to us. Do you understand this? This you had already seen in your real analysis course. Okay, this exercise is already seen in a very special context, but it's the same thing. Okay, now let's look at. Okay, now that we have understood the convergence of a sequence in the metric D, same as uniform convergence on the set X. Okay, there is something very interesting. Okay, let us look at first. Now let us look at Fn. Okay, now you can say when Fn is D quotient in the metric D, D quotient. I'm sure all of you can guess. What do you expect? Fn is uniformly quotient on X. That's it. Okay, so Fn in the metric space is quotient if and only if Fn is uniformly quotient on X. Now we can connect the theorems which you learn in real analysis. What did real analysis theorem say? Real analysis said, okay, if Fn's are continuous functions, okay, and if it's uniformly quotient, then Fn converges to, there is a continuous function F, so that Fn converges to F uniformly on X. This is uniformly quotient. if I have given a uniformly Cauchy sequence Fn on X, then there is a continuous function f such that Fn converges f uniformly on X. I am still working with X metric space. Okay, right. Now Fn is uniformly Cauchy is same as saying Fn is D Cauchy, Cauchy in the metric space. And Fn converges f uniformly is same as saying Fn converges to f in the D metric. So what does it say? It says that the metric space X CXR with the subnorm metric D, this is a complete metric space. Yeah. So it has said that CXR is a complete metric space because you give me any D Cauchy, then it's uniformly Cauchy. If it's uniformly Cauchy, it converges uniformly to a function, right? And that function is continuous because Fn's are continuous. Therefore, F will also be an element of the set. Therefore, Fn converges uniformly same as saying Fn converges F in the D metric. Therefore, any D Cauchy sequence is deconvergent in the space. That means it is a complete metric space. Do all of you understand? Pause, review, and proceed. Now let's come back. So suppose now I have a family F of this metric space Cx. Now I will not mention the metric. I will not even mention Cxr. I will simply write Cx. Okay, a family of functions, continuous function on X. Notice that since X is compact metric space, any continuous function F, okay, any element here, F in Cxr will be uniformly continuous on X. Therefore, F is actually a family of uniformly continuous function. Now what I want to know, I want to characterize compact subsets. Where? In the metric space CXR or CX. Okay. Now since it's a metric space, if F is a compact subset of CX, then what do I know? Necessarily F must be closed in X, because in any metric space a compact set must be closed. And two, in any metric space a compact set must be bounded in X. What does boundedness in X means? It must be with respect to the metric. Therefore, what does it say is, let us look at 0 in CXR. Okay. Therefore, the distance between F and 0 for F in script F, this must be less than or equal to M for every F, which is same as saying the subnorm of F must be less than or equal to F for every F in the family. This is what classically we will call it uniformly bounded. Okay. We have seen already in lecture 1 about this. Okay, this is another necessary condition. To find out, to characterize compact subsets of this, Arzela-Ascoli gives a third condition. So if I assume F satisfies 1, 2, and 3, then F is a compact subset of CXR. That is what Arzela-Ascoli theorem tries to say. Now, what is the third condition? Okay, notice that in the beginning I already said the third condition usually depends upon uniform behavior of the elements of the space. Now, when does a function f from x to r is going to be in Cx? It has to be continuous. In fact, it has to be uniformly continuous because X is a compact metric space. Now I have a family of such things. Now uniform continuity, what does it mean? If you give me an epsilon positive, then there is a delta positive, so that for every x and y in capital X, distance between x and y less than delta should imply distance between fx and fy. That is modulus fx minus fy must be less than epsilon. Right? That is when f will belong to Cx. Any function f from x to r will belong to Cx. Now what do I want is this collection, the family script f should have the uniform behavior. What does that mean? See, each and every element of script, the family f is uniformly continuous. That means for you given epsilon, you give me any f, there is a delta. This delta will depend upon your epsilon and f, so that the delta satisfies the uniform continuity condition. Now what I want is uniform behavior, means this delta will depend only on epsilon. It will not depend on f. That is what is meant by it's uniformly equicontinuous. Okay, we had already defined in the context of R, but let us recall this. What is the third condition? F is uniformly equicontinuous. What does that mean? That means that is for every epsilon positive, there is a delta positive, so that for all xy, so that in x, so the distance between x and y less than delta, what should have? Model for, and for every f in the script f, fx minus fy should be less than epsilon. Usually textbooks will write for every epsilon there is a delta, so that for all x and y, so the distance between x and y less than delta implies mod fx minus fy is less than epsilon for every f in script f. This one usually is written here. Okay, and textbooks may write here, but in MTTS we always write the quantifiers at the beginning. Okay, this is the way. Is that clear to all? Okay. So you can see it's a uniform behavior. Each element must be uniformly continuous, but that means you are given epsilon, there is a delta, but the delta may depend on f. But when I want to say uniformly equicontinuous, this delta should be independent of f. For every f, single delta is going to work. Do all of you appreciate? We had already seen examples in lecture 1, so I'm not going to stop to do such things. Is that all right? So, Arzela-Ascoli theorem, let us state it. Okay. A family F in C of X, okay, with a supermetric is compact if and only if one, F is closed as a subset of the metric space, 2, F is bounded as a subset of the metric space, in classical terminology, which is same as saying uniformly bounded, okay, which I had already defined. Third, F is uniformly equicontinuous on X. Is the theorem clear? These two are expected for any metric space. Third one is uniform behavior of the elements in the allegedly compact subset. We will come to that in another case later, if time permits, of course. Okay, let us start with the proof. Let us prove one way. Let me assume F is compact. Then is one clear? Because F is a compact subset of metric space, and any compact subset of metric space is closed. Therefore, one is clear. And any subset of compact subset of metric space is bounded. Therefore, 2 is also clear. So I only have to check whether F is uniformly continuous on X. Okay, so we need to only check is F uniformly equicontinuous. That's all I have to check. If I have to check its F is uniformly equicontinuous, what is that I have to do? You are going to give me an epsilon positive, then I have to find a delta positive so that something happens. So let epsilon be given, right? Now let's go back. Now F is compact, right? Since F is compact, then F is totally bounded, right? Therefore, for this epsilon, since it's totally bounded, this is by characterization 2, right? By characterization 2. Okay, it's totally bounded. Now I have to exploit the fact it's totally bounded. If I have to exploit the fact it's totally bounded, I have to look for a positive epsilon. Since you had already given me epsilon to check the uniform continuity, uniform equicontinuity, right? Therefore, for this epsilon, what do I know? There exists finitely many functions f1, f2, fn in F, such that my script F is a subset of union fj epsilon. Right? That's what there exists. An epsilon net in F. Call it f1, f2, fn, so that F is contained in this union. Okay? Very good. Now, for each fj and the given epsilon, since F is uniformly continuous, for j only less than or equal to m. Okay, there exists a delta j which ensures uniform continuity of fg, right? But what am I supposed to do? I wanted to prove there is a f is uniformly equicontinuous. That means I have to exhibit a delta which will work for all f in script f. I'm sure by now you know enough training is given in various course of analysis you undertook. What will be your choice? Yes, good. Take delta to be the minimum of delta 1 to delta n. So we want to show then this with respect to this delta, I can prove equicontinuity. Okay, let us do that. To prove equicontinuity, what is that I have to do? You are going to give me an x and y in capital X such that distance between x and y is less than delta. What I have to show? I have to check whether distance between fx and fy is less than epsilon. I'm putting epsilon in quote because it may not be epsilon, it may be some multiple of epsilon, possibly. This should be true for which f? For every f in script f. That's what it will be, uniformly equicontinuous, right? That means I have to estimate distance between fx and fy. I wrote distance, but it is, since these are all real numbers or complex numbers, I can use modulus. So I have to estimate mod fx minus fy. This proof I had already given in I think lecture 1. Yeah, please check that. I am repeating the proof. Okay, anyway. So do I know how to estimate fx minus fy? I do not know. What I know, if you give me an f and f belong to the family f, it has to be in one of the open balls. That means there is a j such that my f belong to b f j epsilon, right? Therefore, I know how to estimate the distance between f and fj, and I know how to estimate fj of x and fj of y because fj is uniformly continuous. You understand? Therefore, we use our curly leaf string. So let us write fx minus fj of x, where f belong to b of fj of epsilon. Okay, and plus fj of x minus fj of x minus f of fj of y minus f of y. So this is less than equal to mod fx minus fj of x plus mod fj of x minus fj of y plus mod fj of y minus f of y. Right? Now f belong to the open ball around fj, epsilon ball around fj. Therefore, the first and the last term independent of x and y, because remember the metric is supernometric. Therefore, first and last term will be less than epsilon. Now, let us look at this, the middle term. Now, fj is uniformly continuous. So, you gave me an epsilon. Therefore, by my choice, there is a delta j, so that whenever distance between x and y is less than delta j, this middle term will be less than epsilon. But remember, my x and y are such that distance between x and y is less than delta, and delta is minimum of all the delta j's. Therefore, distance between x and y is less than delta j, and hence the middle term is also less than epsilon. Therefore, what I have shown? I have shown that mod fx minus fy is less than 3 epsilon. Under what conditions? For any x and y, such that distance between x and y is less than delta. And for what f? For any f in the family script f. So what I have shown? In place of epsilon, I could have taken epsilon by 3 in the earlier thing, then I would have got it. So what I have shown now? The family f is uniformly equicontinuous. So what we have shown now? We have shown that we have proved the necessary conditions. If f is a compact subset of C of x, then f must be closed in the metric space, and f must be bounded, or in classical language, it is uniformly bounded. Third thing is the family f is uniformly equicontinuous on the set x. Is that clear? Okay. Now what remains to be shown? We have to prove these conditions are sufficient. What does that mean? I am going to assume F is a family of continuous functions in Cx and satisfying closed, bounded and uniformly equicontinuous. Then I have to prove it is compact. Is that clear? Now to prove F is compact, what do I have to do? Remember, Cx is a metric space and we know it's a complete metric space, right? And for complete metric space, okay, for a metric space, we know a characterization of compactness. A subset K of a metric space is compact if and only if K is complete with the induced metric and it is totally bounded. But if K is complete, okay, now since C of X is already a complete metric space, to show K is complete, it's enough if I show the family F is closed. But it is given to me. You understand that? Since F is closed in Cx and Cx is complete, F is also complete. Therefore, I don't have to worry about completeness. That's part of my hypothesis. So I only need to show the family F is totally bounded. Do you follow that? Please, if necessary, play it back. Okay. Pause, review, and proceed. So we need only show. So we have to enough to show the family is totally bounded. Okay. Right. If it's this is what I have to show. That means you are going to give me an epsilon positive. Then what I am going to actually show is the following. I am going to show there exists the finite number of subsets U1, Un, which are in C of X. So that diameter of U's are less than or equal to something to this epsilon. May not be epsilon, maybe. And such that my script F is contained in union of Uj, j running from 1 to capital N. Okay, what I'm just giving a strategy of the proof. What I plan to do, I am going to find a certain number of finite subsets U1, U2, N. About the set, I am not making any claim whether it's open, it's closed, nothing. It's just a finite number of sets U1, U2, N. With what property? The diameter is less than or equal to something to the epsilon. Maybe epsilon, 2 epsilon, 3 epsilon, or 10 epsilon. I don't care, some epsilon. And then I will show that this F is contained in this. I claim this is enough to show F is totally bounded. Is that clear? Why? Since I know what I'm going to prove, it's actually diameter of this will be less than or equal to 4 epsilon. Right? Therefore, what can I do now? So what I can do is, if I fix an Fj in Uj and look at the open ball Bfj 5 epsilon if you want, then that union will contain F. Is that clear to all? Because yes, because given any F, it has been on Uj. Right? Therefore, distance between U and distance between F and Fj will be less than 4 epsilon. That means my F will belong to Bfj 5 epsilon. Therefore, my F is containing the finite number of 5 epsilon net. Are you following? Pause, review, proceed. So, what all I have to do therefore is I have to find a finite number of subsets whose diameter is something to do with epsilon. Okay, and my F is contained in their union. How am I going to do that? That's a very interesting thing. Okay, and it's also geometric. In fact, this is by now a very standard proof in many textbook, but I actually found this proof in one of the MTTS camps. Okay, by drawing a picture. I'll draw a picture and I'll try to explain how I got it. So you are given me F is bounded, closed, and uniformly equicontinuous. Right? Very good. And you also gave me epsilon positive to establish the total boundedness. What I'm going to do is, since the family F is uniformly equicontinuous, I want to uh, exploit this epsilon and the fact that script F is uniformly equicontinuous. Therefore, I know there is a delta positive such that blah 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 blah. Okay, all of you know what it means. Okay, since the family is uniformly equicontinuous, for this epsilon there is a delta with whatever, you know this. I am not going to write it. Okay, so I got it. Right, now what I want to do is, so this delta, where does it affect? It affects elements from capital X. This epsilon, where does it affect? It affects elements where F take values from, namely R or C or in a metric space, but let me stick to R. You follow that? So what I want to do is, I want to find, since X is given to be compact, you gave me delta, right? Now X is totally bounded. X is compact metric space, therefore it's totally bounded. I want to exploit this total boundedness using delta. Therefore, I know there exists a finite subset, call it x1, x2, xm in capital X, so that this x1, xm is a delta net for X. This is a delta net. What does that mean? That means X is contained in, it's actually equal to union of B xj delta, where j is running from 1 to m. Okay, good. Now let's look at. Now the next thing is, you told me F is bounded in the metric. That is same as saying uniformly bounded. What does that mean? That means there is an M positive, so that for every F in script F, mod F of X for any X and for every X in capital X, mod F is less than or equal to M. That means each one of the M will take values only from minus M to plus M interval. Or in the compact case, it is the closed disk B0 capital M. Okay, so now I am ready for the picture. Okay, maybe I should go to the next page so that I can write on the picture. So I am going to imagine my X to be the x-axis and my R to be on this, and I have something like M to M, minus M to plus M. Okay, you understand this? Right. So think of this minus M to plus M, or if you want to think of this as 0 is here, somewhere minus M to plus M somewhere. Okay, now I have something like, let me write some different color schemes. I have some x1, x2, x3 and xm. This is the delta. Therefore, if I take delta intervals around this, delta open bars around this, they cover everything. Is that clear? Now I have the compact set, let us say minus m to plus m somewhere. Let me assume this is minus m to plus m from here, so that it will be easier for me, and plus m. Okay, this is minus m. Okay, now I can find some, let me call this as, similarly there exists y1, y2, yn in the interval minus m to plus m, so that the set minus m is contained. Remember, this is a compact set, therefore it's totally bounded. Therefore, for the given epsilon, there is an epsilon net consisting of n numbers in the interval minus m to plus m. Therefore, minus m to plus m is contained in the open ball. Let me write open ball. It's actually in this case in interval. In the complex numbers, it will be open ball, so that yj epsilon, and j is running from 1 to n. Do you understand this? That is the j I am going to do. Therefore, I have something like y1, something like yn. Do you follow that? Yeah. So I use total boundedness of X as well as the image minus m to plus m. Okay, where f of X is contained in this interval for every f in the script family script f. Okay. Now what we want to do is look at this. For this, now let's look at the set of functions. Let me write it A, the set of functions alpha from which set? This finite set of elements x1 to xm, and to which takes values in which set? In the finite set y1 to yn. You understand that alpha is any function from the finite set x1 x2 xm, which is a subset of capital X, to the finite set y1 to yn, which is a finite subset in the interval minus m to plus m. They are all real valued functions. You understand that? Now, typically, suppose I have some xj, this is my xi. Let me write it, sorry. This is my xi, and suppose this is my yj. So this is my xi. This is my yj. So this function alpha takes the value at xi, the value yj, alpha of xi equal to yj. So all possible things. It may be y2, y1, ym. Can you imagine this picture now? Please imagine. Just don't take, just symbolically manipulate. Okay, try to understand. So how many such functions are there? So you notice that for every x1, I could have chosen any one of the y1 to yn. Therefore, n choices. For each one of the xj, I could have n choices. Therefore, the number of elements in A, that is number of such functions, is n to the power m. I hope I am right. Yeah, n. Yeah, n to the power m. You understand that? Now let's look at a function. The function f in this family f, it will be some continuous function. Therefore, it takes values from -1 to plus m somewhere like that. Okay. Now you notice that I can kind of draw some kind of a graph thing. That is, look at this one x1 x2 xn. Look at this. I can't draw pictures very nicely, but just it will be easier if you imagine like this. This is a function. Okay, at each other thing, and here also each of this thing. So some kind of intuitively that I am forming squares. Now it has to lie somewhere here. Do you understand this? That's what we are going to make use. But you don't have to depend on picture. I will prove everything rigorously. Right? Now for each alpha in A, I want to associate set U alpha. What is the U alpha? U alpha is set of all functions f in script f, right? With what property? The property is, look at its value at xi and look at the value of alpha at xi. Okay, this should be less than epsilon. For which I? For every I between 1 and m. You understand this? Again, look at the picture. Okay, this f should have lived somewhere here. For example, here, this may be my xk, this may be my yr. That's where it has to. Is this clear? All right. Two things I want to claim. What are the two things I want to claim? I want to compute that diameter of U alpha. Notice that the number of U alphas are finite because alpha is varies over n to the power m. Therefore, number of U alphas is finite. So what I plan to do is I am going to show the diameter of U alpha has something to do with epsilon, some multiple of epsilon. And second thing I want to prove is script f is contained in union of U alphas. If I have shown by the remark I just made in the beginning of the proof, I would have shown that script, this family f is uniform, is totally bounded. That would complete the proof. Do you follow that? Make sure you understand. Spend some time on understanding alpha. Notice that alpha is no, f's are all uniformly continuous function, but alpha is defined only on a finite set to this. Of course, in the other set it's also continuous. Yeah. Okay. So in some sense, these are all discrete things. Okay, do that. Okay, the first one is very easy. Take F and G in U alpha. What do I want to do? When I want to show diameter of U alpha is finite, for any F and G, I have to say the distance, namely this, okay, this is less than or equal to something, a fixed constant. Then the diameter will be finite. I want the constant to be something to the epsilon. I have to find it, right? Let us do that. So that means what is that I have to estimate? I have to estimate for every x in capital X, I have to estimate what is modulus fx and gx. If I show that is something to do with less than or equal to 3 epsilon, 4 epsilon, 10 epsilon, I am through. A fixed number times epsilon, right? Now, how do I know this? Now notice that F, I do not know how to estimate fx minus gx, but I know f belongs to u alpha. Therefore, I know how to estimate the distance between fx and fxi and alpha xi. You understand this? That means I have to break it into fx minus fxi. But then, how do I estimate fx and fxi? That I do not know how to estimate, but I know how to estimate fx and fxi if x belong to the xi, the delta ball around xi. And do I know that? Yes, because x1, x2, xm form a delta net for x. That means given any x, then there is an I such that my x belong to bxi delta. You understand? Therefore, I know how to estimate f of x and f of xi. Are you following? Don't worry about the textbook proof. Try to think along with me. Textbook proof you can find from a book or from an article or from any other book for that matter. Okay. So I'm trying to give you some idea how to do that. So I break it into various parts. I know how to estimate fx and fxi, where if x belongs to bxi delta. Then what do I know? Since f belongs to u alpha, I know how to estimate fxi and alpha xi. Is that clear now? That's it. We are through now. So this one is less than or equal to mod fx minus f of xi. What is this xi? I'm not writing this xi. What is that xi? X belong to b of xi delta, that xi. It may belong to more than one, but fixed one, right? And then what do? I added, I subtracted, therefore I should add, therefore fxi minus alpha xi. And the next one will be alpha xi minus g of xi plus g of xi minus g of x. Do you understand this? Okay. This is less than or equal to. Now we are through. Why? Look at this. Now x belongs to bxi delta by my choice of delta. Okay, xi form an epsilon. Okay, my choice of delta, and then this shows. Remember again, you are using what is the delta? The delta is you give me an epsilon by equicontinuity. I form a delta. Do you remember that? Do not forget that. You give me epsilon, I form, because uniform equicontinuity, I form the delta. Therefore, my x and xi lie at a distance less than delta by equicontinuity. Whether it is f or g does not matter. Therefore, the first term, okay, is less than epsilon. And similarly, for the same reason, second term is last term, fourth term is also less than epsilon. Do you understand this? Because uniformly equicontinuous. Therefore, x and xi are at a distance less than delta, and g is a function in the family. Therefore, this will be less than delta. Do you understand? Now, what do I know about this? This is very easy because f belongs to u alpha. Therefore, distance between fxi and alpha xi. Let's look at that. For every I, fxi and alpha xi must be less than epsilon. Therefore, the second term is also less than epsilon. And g also belongs to that. Therefore, that term also less than epsilon. Therefore, what do I have done? I have shown that for every x, fx minus gx is less than 4 epsilon. Therefore, if I take supremum or LUB, that will be less than or equal to 4 epsilon. That means the diameter of U alpha is less than or equal to 4 epsilon. That's very good. Good. Okay. So pause, review. proceed. Now I have to prove the second one. What is it I have to prove? I have to prove script f is contained in union of u alphas. Okay, that's again easy. Why? That means you give me any f, all right? Let us look at. I have to say it belongs to ui. What does it mean? Let us look at f of xi. When does f, the function f belong to u alpha? That means fxi minus alpha xi must be less than epsilon, right? Now let's look at f of xi. F of xi belong to minus m to plus m, right? But minus m to plus m is contained in union of b yj epsilon. Therefore, there is at least one j such that f of xi belong to b yj epsilon. Do you understand that? This implies there is a j such that mod fxi minus yj is less than epsilon. This j will depend upon I, right? J equal to j of I. Right? Then what do I do? Now I define alpha. Now we are defining alpha. It will map xi to where? Yj. Absolutely. So for each xi, f of xi belong to this. That means there is a j such that mod fxi minus yj is less than epsilon. So map xi to yj. And that is my function alpha. By very construction, for each I, mod fxi minus alpha xi is less than epsilon. That means my f belong to union u alpha. Do you understand this? Therefore, f belong to u alpha for this alpha. Okay. So what have we shown now? We have shown that f is totally bounded. Therefore, f is totally bounded. We already know it's complete. Therefore, it's closed and hence complete. Therefore, we know it is compact. So Arzela-Ascoli is proved. See, now I want to say two things about thing. First thing is, everybody is now enamored by the compactness by means of open cover, which is very needed, and that's a definition for compactness in a general topological space. But when you want to work with metric spaces, I find the sequential characterization of compactness, namely a set K is compact if only if every sequence Xn has a convergence of sequence converging to an element of the set K. Okay, that is the most useful one. But when I want to prove something to do with compactness, okay, most often the second condition may be used. For example, in equicontinuity, this Arzela Ascoli, what did you do? I wanted to say a family F is compact. Then I didn't use the sequential characterization. I tried to use total boundedness, because total boundedness brings it into something like estimation, analysis, inequality. That becomes easier. You have to believe me. Okay, right. I will tell you why that is important. Just I will start with a very simple minded example. Let us look at the space L1, which is of all sequences an. So that these are all complex numbers or real numbers, okay, sequences. So that it is absolutely summable. That is, this is finite convergent. Okay, you can check this is a vector space, and it's actually this one is a norm. I will call any element like A as sequence an. The norm of A by definition is mod an. This will be a norm. Okay, therefore this becomes a Banach space, in fact a complete metric space with respect to this norm. Complete norm space non-linear space, that means it's a Banach space if you know that word. Otherwise, simply ignore. Please try to understand at least 32%, 30 to 40% of what I'm saying. That's good enough. If you learn functional analysis, you will again come across this, you will understand. Now, what I want, if you give me a subset K of L1, I want to know when it is compact. I want a characterization, like a Haley-Borel theorem for this, or Arzela Ascoli theorem for this. Now, what did I say? Arzela type characterization will imply first condition is K is closed. That's good enough because this is a complete metric space. Therefore, I have to show K is complete. Since L1 is complete, it's enough we show K is closed. And second condition is K is bounded. These are always there in a metric space. The third condition I said will say uniform behavior of elements here. If you give a sequence AN, when does it belong to L1? If it belongs to L1, if summation mod AN is convergent, that is the series is absolutely convergent. Now I have to understand, okay, what is the uniform behavior for all sequences A in K? Okay, right. I will just explain this. And this is the kind of argument you will also read in functional analysis for compact operators, etc. Various results related to compact operators. Instead of sequential definition, if you use total boundedness definition, you will see things come out very neat and easy. You can check our book on functional analysis written by me and Sukumar. Okay, now what is the thing? Now let's look at AN. When I say this is a conversion, look at my Sn. This depends on A. What is Sn of A? This is by definition the partial sum mod AK, K equal to 1 to n. So suppose this sum is convergent, let us call this alpha. Alpha is the sum, right? So what does it mean to say this is convergent? My Sn of A converge to alpha. It's actually alpha of A also, but let me scrap A, simply say Sn converge to alpha, right? Therefore, I want some kind of uniformity. What does it mean? When does I say Sn converge to alpha? If you give me an epsilon positive, there is an n. That n will depend upon the sequence and the series. Therefore, it n depends on A. So that for all k greater than or equal to n, I want modulus of AK, k equal to 1 to n minus alpha. This should be less than epsilon, right? Or the partial sum after nth stage, capital nth stage, must be epsilon close to alpha. Now, what will be my uniform condition? So, for every A in K, I want uniformity. Okay, they all behave in a similar way, uniform fashion. What should be that? That means you give me an epsilon positive. Okay, there exists a capital N, so that for all k greater than or equal to capital N, and for all A in K, this must be true. The partial sums summation k equal to 1 to n mod AK minus alpha should be less than epsilon. You see that? This is the uniformity. A single n is going to work, and usually textbook will write it in the tail condition. This is, they will write something to do with n plus 1 to infinity of mod AK should be less than epsilon for every A in K. That is the tail of the series. Summation n plus 1 to infinity of mod AK should be less than epsilon. This should be true for every sequence A in K. This is a standard formulation you find in textbooks, including in our book. I think this will be the one. Okay. And how to prove that? The way is, if you fix n, notice that A1 to An for any A in A, they all live in a polynomial vector space. Okay. R power capital N. You understand this? Okay. And the tail of the sequence always less than epsilon. And these are a finite thing. They are going to be bounded because you assume they are bounded. Therefore, in Rn, we saw that boundedness is equivalent to total boundedness. Therefore, we can find an epsilon net for any A in here and the first n terms alone. Okay. And the last, the tail, it's independent. I don't choose. Okay. Anyway, think about the proof. I don't want to spend time. And same thing you can do. Look at the sequence C0, which is all A, so that AN converges to 0. What does that mean? For any epsilon, there is an n which depends on A, so that mod AN is less than epsilon. So what should be the third uniform behavior condition? I leave it to you as an exercise. Okay. I hope you enjoyed. I hope you enjoyed. Please go through. Okay. And even for integrability, something similar should exist, but it has been known and proved by Kolmogorov in the case of compact intervals of Rn. Compact intervals of R and for Rn also. You can check that in my compact subsets of LP article. But leave it aside. If you understand Arzela-Ascoli for continuous function and something like Arzela-Ascoli for L1 and C0, you are already on the very nice path. I hope you enjoyed, and I also hope that I gave you a lot more insight than you will find in textbooks and lectures. Okay, think about, go through. As I keep saying, please watch these videos with a small group of like-minded, dedicated students, okay, friends. Then you can discuss. You will see, you will learn a lot more than what I can teach. Okay, that's an absolute truth. Okay, thank you very much. Have a good day. I'll stop.